Navigate through the tabs to understand core F0Z mathematical functions like stabilization. Observe a simplified agent simulation, including flow state adjustments and resource allocation. Review formulas related to advanced concepts such as computational agents and quantum components. Emulation scenario and controls. Simulation scenario prompt. Agents collaborating on a complex scientific discovery. Generate scenario and restart sim. Current scenario. An interdisciplinary team of F0Z agents has been assigned to analyze anomalous data patterns from a collapsed pocket dimension, collaborating to unlock the secrets of its exotic physics and potentially synthesize novel forms of matter. Pause. Step. Reset. Simulation step 2. Agent simulation dashboard. Agent A1. Physics. Flow state, flow. Engagement, 8. Performance, 1.000. Complexity, 0.672. Resources, 16.67. Domain output. Physics log, detected dark matter signature. Energy signature, 10.90 TeV. Confidence, 0.502. Agent A2. Chemistry. Flow state, flow. Engagement, 10. Performance, 1.000. Complexity, 0.969. Resources, 16.67. Domain output. ChemLab sim, reaction, CO2 plus NaCl, H2CO3. Yield, 91.7%. Purity, 30.8%. Performance history, last 5. 1. TA3. Molecular biology. Flow state, flow. Engagement, 10. Performance, 1.000. Complexity, 0.336. Resources, 16.67. Domain output. Bioinformatics core, pathway identification for TP53. Result, variant found at CHR0:66769. Significance, P equals 0.0254. A4. Information theory. Flow state, flow. Engagement, 10. Performance, 1.000. Complexity, 0.063. Resources, 16.67. Domain output. Infosys log, task, entropy analysis. Input size, 182.40 kilobytes. Output/metric, 189.45 kilobytes/7.7. Welcome to the F0Z Agent Simulation Explorer. This application provides an interactive environment to explore the fascinating concepts underpinning the F0Z framework, including its mathematical foundations, core agent behaviors, system-level interactions, computational agent structures, and quantum components. For many of the formulas and concepts, you can click the Explain button to get a detailed explanation generated by Google's Gemini AI. Key notation summary. Key notation summary, stabilization, STAB applied element-wise to prevent numerical instability. Flow control, agent decisions governed by softmax-weighted heuristics and resource constraints. Quantum integration, stabilized quantum state manipulation and hybrid classical quantum learning. Adaptive learning, F0Z gradients and variances regulate optimization dynamics. Domain-specific data, D_IT, represents the unique information processed or generated by an agent based on its specialization, e.g., physics calculations, chemical simulations, creative outputs. F0Z mathematical foundation formulas. Stabilization function, STAB. Explain. STAB x epsilon equals if x epsilon, sign, x, asterisk epsilon otherwise x, with sign, 0, is an element of, 1, minus 1, context dependent, for complex z equals a plus pi, STAB, z, epsilon, equals STAB, a, epsilon, plus I asterisk STAB, b, epsilon. Stabilize. Y, here is an explanation of the stabilization function STAB, x, epsilon. This concept defines a function, denoted as STAB, x, epsilon, designed to prevent input values from being strictly 0 or arbitrarily close to 0, effectively enforcing a minimum magnitude epsilon for values within a certain proximity of 0. It is defined for both real and complex numbers. 1. Core idea and purpose asterisk. The fundamental purpose of STAB, x, epsilon, is to introduce a nonlinearity around 0. His section outlines formulas related to F0Z computational layers, including forward/backward passes and weight updates. These concepts are foundational for agents that learn and adapt through computational processes similar to neural networks, but with specific F0Z stabilization mechanism. Quantum components. Explore formulas pertaining to quantum state stabilization, measurement probabilities, quantum Q functions, VQC, and curiosity rewards within the F0Z framework. These highlight the integration of quantum mechanical principles for potentially enhanced computational capabilities or novel agent behaviors. Q_STAB. This concept describes a method for generating an intrinsic reward signal in agent-based systems, primarily within the framework of reinforcement learning, RL, known as curiosity reward. Its core purpose is to drive exploration by incentivizing the agent to seek out novel or unpredictable experiences in its environment. 1. Core idea and purpose asterisk. The fundamental idea is to provide the agent with an internal reward signal, R_int, that is independent of any external, task-specific reward. This intrinsic reward is generated based on the agent's surprise or the unpredictability of the environment's response to its actions. When the environment transitions to a state that is difficult for the agent to predict, the agent receives a positive intrinsic reward, encouraging it to visit such states more often. This mechanism is particularly valuable in environments with sparse, delayed, or non-existent external rewards, where blind exploration might be inefficient or impossible. It fosters an agent that is motivated to learn about the world's dynamics. The concept of a F0Z layer forward/backward pass describes the fundamental computational steps performed by a single layer within a computational model, likely a form of neural network or a similar layered architecture used in frameworks like F0Z. The core idea extends the standard operations of a typical artificial neuron layer by incorporating a stabilization function denoted as STAB, x, epsilon. 1. Core idea and purpose asterisk. The primary purpose of a F0Z layer is to perform a transformation on its input activations, A_L1, to produce output activations, A_L, while critically ensuring numerical stability or maintaining values within a constrained range during both the forward computation and the backward propagation of gradients. The stab x epsilon function, parameterized by epsilon and epsilon_grad4 gradients, is the key mechanism for this stabilization. It likely represents some form of clipping, scaling, or thresholding operation designed to prevent values, like pre-activations or gradients, from becoming excessively large or small, which can lead to issues like numerical overflow/underflow, exploding/vanishing gradients, or instability during learning. Typical application or significance ***. The F0Z layer, with its integrated stabilization mechanism, is significant in computational contexts where strict control over numerical values and stability during computation and learning is paramount. This could include agent-based systems, particularly those where agents operate with limited computational precision, bounded state representations, or require robust and predictable learning dynamics in potentially volatile environments. If agents' internal models or control policies are based on neural networks, enforcing value constraints via stab can be crucial for their effective and reliable operation. Explanation: measurement probability. Okay, here is an explanation of the concept measurement probability based on the provided formulas, suitable for a university student or researcher in computer science and mathematics. This concept describes a probabilistic measurement process applied to a system in a given state, drawing heavily on principles from quantum mechanics while introducing a non-standard modification to the probability assignment. 1. Core idea and purpose ***. At its core, this concept defines how the outcome of a measurement is determined probabilistically and what happens to the system state after the measurement. It follows the general structure of quantum measurement but introduces a specific function, stab, to potentially modify the standard probability distribution of outcomes. The purpose is likely to model measurement processes where the ideal, born rule, probabilities are altered by factors such as thresholds, nonlinear processing, stability considerations, or noise, controlled by a parameter epsilon_p. This allows for modeling scenarios where small probabilities might be suppressed or amplified in a non-standard way before the outcome is stochastically selected. 2. Key mathematical principles and mechanisms ***. System state ***. The system is assumed to be in a state represented by a state vector psi, likely residing in a vector space, analogous to a Hilbert space in quantum mechanics. Measurement outcomes and basis states ***. The possible outcomes of the measurement are associated with a set of distinct states, represented by basis vectors I. A measurement projects the system onto one of these basis states. Amplitude and ideal probability. Born rule: the term I psi represents the projection of the state psi onto the basis state I. Its magnitude squared, I psi caret 2, corresponds to the standard probability of obtaining outcome I according to the Born rule in quantum mechanics. This is the probability in an ideal, standard projective measurement. Modified probability distribution, P(I), the first formula, P(I) equals stab, I psi caret 2, epsilon_p, introduces a transformation. The function stab takes the ideal Born rule probability I psi caret 2 and a parameter epsilon_p to produce the actual probability P(I) of observing outcome I. The nature of the stab function is not explicitly defined, but its name and the parameter epsilon_p suggest it might implement a form of stabilization, thresholding, or nonlinear mapping of the ideal probabilities. Epsilon_p acts as a control parameter for this transformation. The set of values P(I) for all possible outcomes I forms the effective probability distribution P. Stochastic outcome selection ***. The first part of the second formula, MP, signifies that the observed outcome M is selected randomly according to the modified probability distribution P. This is a standard stochastic sampling process. State collapse ***. The second part of the second formula, psi_post equals M, describes the state of the system after the measurement. Once the outcome M is observed, the system state instantaneously collapses or transitions deterministically to the corresponding basis state M. This aligns with the standard projection postulate of quantum measurement. 3. Typical application or significance ***. The quantum Q function, VQC, is a fundamental building block in quantum reinforcement learning, QRL. Its typical applications include function approximation in QRL agents. It replaces the classical function approximator, like a neural network, used to estimate Q values in algorithms such as quantum deep Q networks, QDQN, or other value-based QRL methods. The agent uses the computed Q_stab, SA, values to determine its action policy. Hybrid quantum classical algorithms. This approach is inherently hybrid. The quantum circuit prepares the state and computes the expectation value, while classical computation handles the encoding theta, SA, optimization of VQC parameters theta, the stab function, and the overall RL algorithm logic, e.g., experience replay, policy updates. Agent-based systems in quantum contexts. While classical agent systems operate in classical state spaces, QRL can be applied to agents operating in or interacting with quantum environments, or simply using quantum computation for enhanced decision-making in complex classical environments. The Q function provides the necessary mechanism for the agent to evaluate potential actions. Exploration of quantum advantage. By using a VQC, researchers explore whether the specific properties of quantum computation, superposition, entanglement, can lead to better performance, e.g. faster convergence, improved sample efficiency, ability to represent more complex functions, compared to classical function approximators for specific types of RL problems or data distributions. In summary, the quantum Q function, VQC, represents a quantum-enhanced method for estimating state action values in RL, leveraging parameterized quantum circuits to encode state action information, perform quantum computation, and derive a classical Q value through measurement and post-processing.